We spent decades hunting weakly interacting massive particles, WIMPs, assuming they make up missing dark matter. But as detectors grew more sensitive, they recorded absolutely nothing. We've looked to the sky for secondary signals, expecting to find gamma rays produced when dark matter particles annihilate each other in deep space. Instead, observatories have consistently reported stringent null results. Plotting mass against cross-section reveals a stark reality. Fermi-Lat and CTA data pushed the viable WIMP space into an impossibly small corner. This forces a pivot to a new candidate, the Axion. We must shift our search down to the 10⁻⁷ electron-volt mass range. Because particle mass correlates directly to signal frequency, hunting for a 10⁻⁷ electron-volt particle means listening for a highly specific electromagnetic frequency, 42 MHz. With the WIMP parameter space effectively closed, experimental physics has to entirely redesign its detection architecture. We are no longer building giant vats of liquid xenon to catch heavy collisions. We must build hypersensitive radios tuned to 42 MHz. The standard tool for this job is an Axion haloscope. It traditionally uses a microwave resonant cavity placed inside a strong magnetic field to capture axions converting into detectable photons. But there is a geometric limitation. A cavity's resonant frequency is inversely proportional to its physical size. Scaled to target 42 MHz, the detector becomes the size of a building. It is physically impossible to maintain a uniform magnetic field across that massive volume. To bypass this, researchers proposed a new class of detector known as a control-toe haloscope. Instead of relying on an empty cavity, this approach uses lumped element superconducting LC circuits. The ADMX SLIC experiment targets this architecture, swapping the massive dimensions of a cylinder for the compact tunability of a superconducting LC circuit. The mechanism that makes this radio detection possible is the Primakov effect. When an axion passes through an intense magnetic field, it couples to two photons, forcing the invisible particle to convert into a single detectable photon. If axions exist, the Ampere-Maxwell equation gains a new term. An axion field acts as a source current. The axion field A moves through a static magnetic field, B0, creating a faint oscillating current, JA. This specific conversion process operates in the quasi-static limit. It requires the physical scale of the external magnetic field to be much smaller than the wavelength of the incoming axion signal. The hardware functions as an environmental trigger, using extreme magnetic pressure to translate the ambient axion field into a measurable oscillating flux. This diagram displays the ADMX SLIC experimental insert inside a 4.2 Kelvin cryogenic shielding can. The outer gray superconducting solenoid magnet generates a 7 Tesla field. Inside, a rectangular primary loop antenna captures axion-induced flux, while a top-mounted rotary piezoelectric motor physically tunes the circuit's frequency. By mechanically altering the capacitance with that alumina sheet, the team tuned the resonant frequency of the entire circuit. This allows for frequency shifts without needing to expand the physical volume of the detector. To successfully amplify a microscopic axion-sourced current, the circuit requires a high-quality factor, or Q factor, ideally greater than 10,000. This presents an inherent engineering conflict. The Primakov conversion demands massive magnetic fields to trigger the reaction, but those same strong magnetic fields degrade the superconducting materials required to maintain high Q factors. This chart tracks transmission measurements as the magnet powered up from 0 to 4.5 Tesla. Notice the distinct frequency shift and the severe degradation of the peak height from left to right. The Q factor ultimately plummeted to roughly 2,500. While the magnetic penalty is severe, documenting the specific electrical loss in high-field superconducting LC circuits provided a vital baseline for future designs. Once an axion creates a signal, the next challenge is extracting that fragile, low-frequency current out of the 4.2 Kelvin cryogenic environment without burying it in thermal noise. This flowchart maps the receiver chain. The signal starts in the 4.2 Kelvin zone at an ultra-low noise amplifier. It travels into a room temperature environment to a secondary post-amplifier. Finally, a mixer uses heterodyning to step the 42 MHz frequency down to 10 kHz. Stepping the signal down to 10 kHz is essential. It allows the fast Fourier transform spectrum analyzer to process the incoming signal into ultra-narrow 31.25 Hz bins, maximizing the chance of isolating a dark matter anomaly from the background static. Ultimately, detecting an axion is a battle of the signal-to-noise ratio, governed by the Dike radiometer equation. The limits lie in the denominator, featuring Boltzmann's constant, K, and system noise temperature, T. For ADMX SLIC, noise temperature was 23 Kelvin, dominated by Johnson voltage noise. The weapon against that noise is integration time. By averaging 10,000 individual scans at each step, the random fluctuations of thermal noise are forced to flatten out mathematically. This allows a continuous axion signal to theoretically pierce through the static. The depth of any dark matter search is constrained by this math. It depends on how long researchers can afford to sit on a single frequency, while fighting the baseline thermal radiation emitted by the equipment itself. This single exclusion plot combines all measurement runs. The top yellow cast band represents previous limits. The bottom dark green KSVZ line is the ideal coupling strength. The jagged blue line represents achieved limits, with upward spikes indicating where terrestrial radio noise corrupted the search. Here, in the isolated 4.5 Tesla plot, the gap between the blue RFI line and the lower orange line indicates the depth the system would achieve if terrestrial interference were completely shielded. While ADMX SLIC did not reach the KSVZ coupling models, it successfully excluded parameter space below 10⁻12 inverse giga-electronvolts. The experiment establishes a functional blueprint for low-frequency haloscopes, documenting the specific radio interference and magnetic constraints that larger-scale detectors will need to overcome.